This is advanced functions video on 6.6, modeling with trigonometric functions. And modeling means word problems. An ocean tide is an example of a natural event that repeats in a regular and predictable way, so it's periodic. The world's highest tides occur at the Bay of Fundy. Notice in the following data, so on the next screen you're going to see some data. It's for Hopewell Cape, New Brunswick, which is on the Bay of Fundy. The maximum heights are not the same or the minimum heights. So we need to make changes because when things really occur in nature and not in a controlled environment, numbers are off a little bit. They're not perfectly sinusoidal all the time. So we're going to make a few adjustments. So here is a picture of Hopewell Cape. These are called the flower pots, these islands, these towers. And these are actually two of my kids when we went a long time ago. This was low tides. You're standing right on the ocean floor. Bay of Fundy, a little bit of geography for you. This blue section here is the Bay of Fundy. And right in the corner, right up at this edge here is where Hopewell Rocks are. That's where you can walk on the ocean floor because the tide goes out. And this is when the tide has come back in at the same location. So here is some data from February. But if you look at the period of the high tides, so here's a high tide, and here's another high tide. Now they're not exactly the same. To make it easier to work with, we're going to assume the period is 12 hours. So this one was at 10:54 a.m., this one at 11:19 p.m., not quite 12 hours. The second high tide would occur at 10:54 p.m., right? So if we're going to try and make a model out of this, but we're going to adjust some numbers a little bit. The height of that tide would be 11.43 meters to make it easier to represent. And we're going to use this data to predict the height at 3 o'clock p.m. on February 21st. So we need to come up with an equation based on this chart. We need a formula. We might use sine, we might use cos. That's why I kind of wrote it like that. We haven't decided yet if it's sine or cos. But we need to know what A, K, D, and C are. And I use variables that are appropriate for the question, height at time, H at T. So A, remember, A is, we're going to take the positive value of A right now, the amplitude will be positive. It's max minus min divided by 2. Max minus min divided by 2. So what is the max and what is the min? The maximum is 11.43 and the minimum is 2.12. Those are the heights, and then we divide that by 2 and we get an amplitude of, should be an equal sign there, 4.655. Next is the C value, and the C value comes from a max plus min divided by 2. So we're going to do the same thing here, except we're going to just put a plus sign in between. Max plus min divided by 2, and we'll get 6.775. K value, the formula for the K value is 2 pi divided by the period. So what is the period? 2 pi divided by, what is the period? The period is 12. Circled there in the question, that's the period is 12. So 2 pi divided by 12, that's going to give us pi over 6 when we reduce. The other parameter we haven't talked about yet is D. What is D equal to? So D depends on whether you're using sine or cosine. D is your phase shift, your horizontal displacement. If we are going to use let's talk about cos first. Cos is usually the easiest because to write an equation with cos as opposed to sine, to write an equation for cos, all you really need to find is the first maximum or the first minimum, and then you would use a negative a value. So cos is usually easier to find. And since the data we're given begins at high tide, that's a maximum, So our t at 0, our time 0 that we're starting with, high tide, the first piece of information we're given is a maximum. So since our data begins at a maximum, we will use cosine. We're going to use cosine, and let me just quickly go over the reason for that. Here is the parent function cosine. The cosine wave looks like this. It starts at a maximum on the y-axis. Cosine has a maximum, its initial value is a maximum. So since this graph about the tides also its initial value is a maximum, we won't need to look at taking this red wave and shifting it to the right or shifting it to the left, because our data also begins with a maximum. So we're going to use cosine, and we're going to say our d value over here on the right, d value is 0 because we're using cosine. So that's the easiest way to do it. If the question doesn't tell you, you have to use sine or cosine, and you can pick whatever you want. We want to pick the easiest one. So our equation is going to be h at t equals, our a value is, we'll put a 4.7. So there were decimals in the question all over the place. We have decimals in the time and the height, so we can certainly use decimals in our answer. Cos, my k value is pi over 6. And then I would put, well, I'll just put it in here, t minus 0, bracket plus c, and our c I'll round to 6.8. So this t minus 0 right here, I'm going to change that right now because I don't need to have t minus 0. I can just, and I can even take out these extra brackets and just put this here, plus 6.8. So you don't have to put t minus 0, I just did to show you that my d value was a 0. So I put that in initially, but it doesn't need to be there. So the question says, use the data to predict the height at 3 p.m. on February 21st. So 3 p.m. on February 21st is somewhere in here, right? It's in between 10:54 and 5. So we're trying to use the data to predict the height of the tide at that time. And we've got an equation now that we can use. So 3 p.m., I'm not going to sub in a 3 into my equation. At 3 p.m., it's 4 hours and 6 minutes past our initial time. Our initial time was at 10:54. So that's like our time, that's t equals 0. 10:54 is t equals 0. So at 3 p.m., that's 4 hours and 6 minutes after this time. So that means t equals 4 and 6 over 60, not 4.6, because time isn't one of our metric values. It's out of 10. Values of 10 are factors of 10. So let's just reduce that. And since everything else is in decimals, we could also write that as a decimal, 4.1. So what we're going to be doing is subbing in the 4.1, not 3, subbing in 4.1 right here. So I've already filled that in. There's my 4.1. Now on your calculator, order of operations, first thing you're doing is this bracket, the square bracket. That will be your first thing. Once you get that number, you're going to find cos of it. The second thing you're going to do is cosine of that number. Then the third thing is to multiply by 4.7. And the last thing is the addition subtraction. We're going to add 6.8 on. Once you do all that, you get approximately 4.2. So we have a sentence. Therefore, the tide's height will be approximately 4.2 meters at 3 p.m. If you've ever gone here, or anywhere where you're interested in seeing how the tide, when the high tide and low tide is, certainly there's a lot of professions that are interested in that. You'll always find charts everywhere. And before the internet, the charts were posted on the sides of buildings and on billboards all over the place so that people would know when high tide is and when low tide is. So it is a very common application of a sinusoidal function. Next example. A rocket is launched vertically upward. Nathan is at an observation station 100 meters away. So here's Nathan over here. Nathan measures the angle of elevation of the rocket as it rises. That's X right here is our angle of elevation. Write the height of the rocket as a function of the angle of elevation using appropriate variables. So I'm just looking at part A first. The diagram right here shows a right angle triangle, so that's great. We can use SOHCAHTOA when we have a right angle triangle. The angle is on the diagram here. Here's the angle right there. We've got 100 meters. That would be the adjacent side. H is what we're looking for. That's the opposite side. And of course the hypotenuse, that's not really part of our question. We don't need to worry about it. So which of the three primary trig ratios, sine, cos, or tan, are we going to use? Yes, everyone's thought about an answer, I'm sure, and it is tan. So tan of x is equal to h. H isn't hypotenuse, h is height. That's the opposite over the adjacent 100. Now we need to isolate h. So to isolate h, I'm going to multiply my 100 up. I'm going to multiply both sides by 100, and I will get 100 times tan x. So we've got two unknowns here, equals h. So we've got h isolated, and the question just, the reason I did that was because the question said, write the height of the rocket as a function of the angle of elevation. So I needed to get an equation, a formula for the height of the rocket, and I'll just put that in proper notation here. H at x equals 100 tan x. So we've created an equation, we've modeled an equation from a word problem and a graph. So that's all we had to do there. Before we go on to part B though, one thing I just want to note about part A, think of the tan graph. Think of when we graphed that tan graph, and that weird one, it had a period of pi and it had a whole bunch of vertical asymptotes, right? So the first vertical asymptote, the first positive vertical asymptote we had in that is at x equals pi over 2, which is 90 degrees, but if I convert that to decimals, because we do have decimals in our question here in part B, so if I convert that to a decimal, it's 1.57 approximately equal to 1.57. So when we look at part B, it says graph the function in part A, so we're going to have to graph a tan graph for reasonable angles of elevation. So we're given a restricted domain here from 0 to 1.5. So we have an asymptote at 1.57. So these are reasonable angles of elevation, because if you think of pi over 2 as 90 degrees, that angle is becoming too large to be practical, right? You can't tilt your head up to a 90-degree angle. So here's poor Nathan over here, and this angle right here can't be 90 degrees. We can't have that. So we have a restricted domain right here. So let's talk about part B. So we've got a graph. We're going to graph this function here. That's what part B is asking us to do. So we need to think about our x and y axes here. Let's talk about our independent and dependent variables. The x-axis we're going to draw along here, x-axis and a y-axis. The x-axis is the angle of elevation. They already gave us an x, so I didn't have to think too hard about that. The x-axis is the angle of elevation, and my axis only needs to be from 0 to 1.5. It's given to me in the question. I don't have to make it any longer than that. My y-axis is, of course, h at x or y. And that's going to be the height. That's the other variable in the question there. That's the height. So what kind of height numbers do we need? How am I going to figure out what to put in for a scale here? So I've got the x-axis figured out. What about a scale for the y-axis? So let's calculate a few coordinates just to get a bit of an idea here. So I'm going to calculate some coordinates. So I know height is my vertical axis, and I know angle of elevation in radians will be my horizontal axis, but I want to get an idea of what kind of scale to use. So let's get some coordinates. For example, well, we have a restricted domain, so the first one we can do is 0, 0. Sorry, sub in is 0. I gave you the answer there. Sub in is 0. You get 100 times tan of 0 So that's going to give us 0, 0. So we're going to get the coordinates 0, 0. Let's do a few more. H at, we don't have very many, we don't have a lot of numbers we can use here, 0.5, and then we'll go up to 1, and we'll do 1.5. So I want you to calculate those, press pause, and then come back for the answers. So now we have an idea of what we can use for our scale. We got 1.5 to be 1,410, so now we can put a scale on everything. Another thing I want to try, just for interest's sake, just to show you what would happen if we tried the asymptote. If you subbed in h at 1.57, what are you getting when you sub that number in? So what you're telling me right now is what's the behavior close to the asymptote. So what's going on close to the asymptote? You're getting positive infinity. So here's our asymptote. I don't need that there. Here's our asymptote at pi over 2, which isn't in our domain, I know, but this is worth it to just talk about it for a second. So I know that my graph is approaching infinity as we get really, really close to that asymptote. So obviously if you just subbed in 1.57, you were a little bit to the left of the asymptote because pi over 2 is 1.57. There's more decimals after that. So you're getting really, really close to the asymptote. So that's an interesting piece of information to know. So now that we have our scale, our grid all set up, we can put our dots on and graph it. So I just added on my scale here. You can see I'm counting by 125s. You don't have to count by 125s. You could set it up a little cleaner than that, but that's so you know where I'm coming from. The next point I'm going to graph is 0.5 and 54. That's pretty low down there. So there we have the graph showing the angles of elevation against the height of the rocket. The symbol, or the hertz, the symbol capital H, lowercase z, is unit of frequency from the International System. I just got this from Wikipedia, right? What does hertz mean? It's defined as the number of cycles per second of a periodic phenomenon. So some of you will have already worked with hertz in maybe physics, but some of you won't. It doesn't matter. One of the most common uses is a description of sine wave, particularly those used in radio and audio applications, such as the frequency of musical tones. There's a capital H in it because it's named after Heinrich Rudolf Hertz. So that's just some background information. That's just telling you what hertz are in case you didn't know. So I've got a salesperson, Khalid, and he's selling a car alarm. And he reports that the sound has a minimum frequency of 250 hertz, a maximum being 1150 hertz. Khalid also reports that the car alarm reaches its maximum frequency after 1 second, and the frequency increases as soon as the alarm is triggered. That's important. So the frequency is increasing as soon as it's triggered, and then it decreases and it cycles through from max to a min, max to a min. First thing we're going to do is sketch the graph of the frequency in hertz as a function of time in seconds. Okay, to sketch the graph, we need, the great thing about sinusoidals is you don't need much information to sketch the graph. And we've got the maximum frequency occurring after 1 second. So we know we have a maximum value at 1,150. What are our axes going to be? What's our vertical and our horizontal axis going to be? The vertical will be hertz and the horizontal will be time. If you have a choice between time and anything else, time is always the independent variable. It's always going to be down there on your x-axis. So now we need a scale. It says it takes 4 seconds to cycle through. And this point we have here is we have a maximum at 1 second. So the next maximum isn't going to occur at 4 seconds, it's going to occur at 5 seconds. So I'm going to make my scale here to 5 or 6 seconds down there. Now my frequency, my vertical axis, or my dependent variable, I've got a minimum and a maximum. So I know I only need to go in between those two numbers. if I started my y-axis right at 250, I would have to put a break in the graph. I'd have to put that little zigzaggy thing to show that I'm compressing the y-axis scale. But I don't need to do that really. I'm going to include numbers that I don't need below 250, but it's okay, it spreads out well. So I've got my minimum on here and I've got my maximum up here, and there's my time. So the next thing I need to do is get a point on there. So I have a maximum at 1 and 1150. Let's put that on. So I've got my first point on, and I know that I will have another maximum exactly 4 seconds after that. So 4 seconds after 1 second is 5 seconds. So at 5 seconds, I'm right back up there at my maximum again. And I know exactly halfway between those, halfway between 1 second and 5 seconds, we will have a minimum. So all I started with was this point. 4 seconds later, I'm back there again. Halfway between these two, I'm at a minimum. So that's going to be at 3 seconds. So I know from the question my minimum is 250 hertz. So at 3 seconds, I'm putting a dot on at 250. And I also know that halfway between a max and a min, I will be along the equation of the axis. I'll be along that horizontal kind of fold line. So halfway between 1 second and 3 seconds is 2 seconds. So I can go halfway again. So that's at 700. So halfway between 250 and 1150 is 700. That occurs again at 4 seconds. So now I've got the 5 big points on, the 5 main points for my wave. I've got max, min, and equation of the axis. And I'm going to draw a curve to connect all that. I'm also going to back it up to get it on the y-axis. And that'll be important in a second here. So let me just put in my wave here. Because I know that every 1 second something important is happening, right? Every second. So at 1 second I'm a max. The next second later I'm halfway. Then I'm at a min. Then I'm at the equation of the axis. Then I'm at a max. So that means if I back it up by a second, at 0 seconds I will be right here on the equation of the axis. That's going to be helpful for part B when I have to come up with an equation. It's helpful to look at a graph to know where you're starting on the y-axis. So there's part A. We've sketched the graph. Part B says state an equation to model this situation using both sine and cosine. So there's our formula. I used F for frequency and T for time. And I'm going to have to use both sine and cosine, but all the other parameters are in the same spot, whether I'm using sine or cosine. So let's get the parameters first that are the same, whether I'm using sine or cos. That's everything except D. D value is the one that changes. So first, A, the positive A value we're going to use, or the amplitude. And you could see that by looking at the graph. If you do a little dotted line across your equation of the axis here, you don't have to actually do the formula calculation. The amplitude, if you remember, is this distance from a max or a min to the equation of the axis is the amplitude. So that is 450. That's what the amplitude is. The C value, I just drew a dotted line right there, or you could use the formula. The C value is 700. The K value, so we're looking for a positive K value here. That's 2 pi divided by the period. So what is the period? The period is 4, so we reduce that and we get pi over 2. So those 3 parameters are done. The D value changes whether we're doing sine or cosine, and for this question we have to do both of them. So let's start first with the easiest one in this case is sine. And the reason the easiest one is sine, let me draw a little sine wave for you here. The sine wave is like this. So on the y-axis, the sine wave begins right at the equation of the axis. It begins at the intersection of the equation of the axis and the y-axis, which is exactly what we have happening here. So the sine wave, the parent function, we see no shift. From the parent function to this function over here. It hasn't shifted. So we're going to do a sine equation first. F at t equals 450, that's our a value, and this time we're doing sine. So in the brackets, all I have is my k value, which is pi over 2, and t, because my d value is a 0 this time, plus 700. Now, if you wanted to, you could have used this d value right here that I'm circling on the graph. This could have been your d value, which is a 4. It would have given you the exact same answer because of the infinite and repetitious periodic form that sine is in. There's a lot of different ways you could write it, but usually we try to keep it simple. So that is one way of writing sine with sine. Now let's try writing it once with cos. F at t equals 450 cos. And our k value is, I'm going to use a square bracket this time because I need a d. So pi over 2 bracket t. Now I need something in there. Let me just close that up for a second. Plus 700. So I'm looking for the d value. For cosine, it's always easiest to find the first maximum. Here's our first maximum. Because the cosine parent graph starts at a maximum on the y-axis, we just want to see where did that maximum go. So instead of having a maximum on the y-axis, it got pushed over to 1. Sorry. So that's going to be t minus 1. And that is a cosine graph. You could also have used this one if you wanted. And in the brackets, you would have had t minus 5. Infinite choices there. So that's what we have for part B. Part C is the last part, the last example for today. And it says, what is the frequency of the alarm at 1.2 seconds, round to the nearest tenth? That's just substitution. F at 1.2. You can pick whichever equation you like. If I was in class right now, I'd have half the class sub it into the sine and half sub it into the cosine. And what a surprise, we would get the exact same answer. So pick one of these two equations right here and sub in 1.2 and come back when you're done. So remember, the order is this multiplication, then by the function, and sine in this case, then multiply by 450, and then last is to add on your 700 at the end, and you should get f at 1.2 equals 1,128. Let's put to the nearest tenth, the question says, so that's a 0.0 hertz. And then a sentence to go with it. Therefore, at 1.2 seconds, the frequency is 1,128 hertz. So there you go with your lesson on modeling word problems. Under 30 minutes. That's pretty good. Good luck.